Once upon a time, the ancient view of our world was vastly different from what we understand today. For centuries, humans looked at the world around them and saw a flat plane. This made sense. After all, our senses tell us that the Earth is stable and unmoving, while the sun and moon appear to move across the sky. Ancient civilizations often incorporated this seemingly flat Earth into their mythology and cosmology. The Egyptians, for example, envisioned the sky as a dome supported by pillars, with the Earth as a flat surface below. Similar beliefs were found in Mesopotamian, Indian, and Chinese cultures. These early models of the cosmos were based on observation and human experience. They lacked the tools and knowledge to understand the true nature of the Earth and its place in the universe. The transition from a geocentric to a heliocentric worldview was a gradual process, marked by scientific discoveries and intellectual revolutions. The idea of a spherical Earth began to emerge in ancient Greece. Pythagoras, in the 6th century BC, is often credited with first proposing a spherical Earth. He, and later Aristotle, observed that ships disappeared hull first over the horizon, suggesting a curved surface. Aristotle also noted the circular shadow cast by the Earth during lunar eclipses, further supporting the idea of a spherical Earth. However, these ideas were not immediately accepted by everyone. The weight of tradition and the lack of concrete evidence meant that the flat Earth model persisted for centuries. It wasn't until the time of the ancient Greek astronomer Ptolemy in the 2nd century AD that the geocentric model, with a spherical Earth at its center, became widely accepted in the Western world. This model, while inaccurate in placing the Earth at the center of the universe, was nevertheless a significant step towards understanding the true nature of our planet. The belief in a flat Earth might seem like a relic of the past, but it has experienced a resurgence in recent times. The modern flat Earth theory gained traction in the mid-20th century, largely driven by the work of Samuel Shenton and his International Flat Earth Research Society. This resurgence was fueled by a rejection of mainstream science and a distrust of government institutions. Modern flat earthers hold a variety of beliefs, but most agree that the Earth is a flat disk, often depicted with Antarctica as a massive ice wall surrounding the circumference. They believe that the sun and moon are much smaller and closer to Earth than scientists claim, circling above the flat plane like spotlights. Gravity, in their view, is either an illusion or works differently than the scientific explanation. The reasons for the persistence of these beliefs are complex and multifaceted. Some proponents are drawn to conspiracy theories and see the flat Earth as the ultimate proof of a grand deception orchestrated by governments and scientific organizations. Others may be motivated by religious or philosophical beliefs that contradict the scientific consensus. The internet and social media have played a significant role in amplifying these ideas, creating echo chambers where misinformation can spread unchecked. The evidence for Earth's spherical shape is overwhelming and comes from various fields of science, including astronomy, physics, and geography. One of the simplest pieces of evidence is the observation of ships disappearing hull first over the horizon. If the Earth were flat, ships would simply get smaller and smaller as they moved away, but we see them gradually disappear from the bottom up, indicating a curvature. Another piece of evidence comes from lunar eclipses. During a lunar eclipse, the Earth passes between the sun and the moon, casting a shadow on the lunar surface. The shape of this shadow is always round, regardless of the Earth's orientation, which is only possible if the Earth is a sphere. If the Earth were flat, the shadow would be elongated or elliptical depending on the sun's position. Furthermore, different constellations are visible from different parts of the Earth, a phenomenon that would not occur if the Earth were flat. The angle of the sun's rays also varies depending on latitude, leading to different seasons and climate zones. This variation in solar intensity and day length would not be possible on a flat Earth. Gravity is one of the fundamental forces of nature, and its understanding is crucial for debunking the flat Earth theory. Isaac Newton's law of universal gravitation states that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between their centers. This means that objects with more mass exert a stronger gravitational pull. In the case of Earth, its large mass creates a gravitational force that pulls everything towards its center. This is why objects fall to the ground when dropped, and why we experience weight. This gravitational pull is consistent with a spherical Earth, where all points on the surface are roughly equidistant from the center. The flat Earth model, on the other hand, cannot adequately explain gravity. If the Earth were a flat disk, gravity would pull everything towards the center of the disk, not straight down as we experience. This would mean that objects further away from the center would feel a pull at an angle, eventually sliding towards the middle. Moreover, the flat Earth model fails to explain how the sun and moon would stay suspended above the flat plane without falling down. Without the force of gravity acting towards a central point, there is no mechanism to keep these celestial bodies in orbit. In Section 5, titled Beyond the Curve, addressing other flat Earth claims, we dive deeper into the theory. Beyond the central tenets of a flat Earth and a lack of traditional gravity, the theory also attempts to explain away other observed phenomena, often with convoluted and contradictory arguments. For instance, flat earthers often claim that satellites are fake and that GPS signals are ground-based. However, this ignores the vast amount of evidence for the existence and functionality of satellites, including their use in communication, navigation, and scientific research. Another common claim is that space travel is a hoax and that images of Earth from space are fabricated. This conspiracy theory disregards the countless hours of work, technological advancements, and international collaboration involved in space exploration. It also ignores the fact that multiple countries, including those who are often portrayed as rivals, have independently developed space programs and confirmed the spherical shape of Earth. Flat Earthers also struggle to explain the existence of time zones, which are a direct consequence of Earth's rotation. They often resort to ad hoc explanations, such as claiming that the sun is a spotlight that moves across the flat Earth, illuminating different regions at different times. However, this explanation fails to account for the consistent pattern of time zones, the gradual transition from day to night, and the observation of different constellations from different parts of the Earth. In Section 6, we explore the psychology of belief, why flat Earth theories persist. The persistence of the flat Earth theory, despite overwhelming evidence to the contrary, highlights the powerful psychological and social factors that can shape our beliefs. One factor is confirmation bias, which is the tendency to seek out and interpret information in a way that confirms our existing beliefs, while ignoring or downplaying evidence that contradicts them. Flat Earthers often latch onto anecdotal evidence or isolated anomalies that seem to support their worldview, while dismissing scientific explanations as part of the conspiracy. Another factor is the desire for simplicity and certainty. The world can be a complex and confusing place, and for some, the flat Earth theory offers a sense of order and control. It provides simple answers to complex questions and allows individuals to believe they possess secret knowledge that most people are unaware of. This can be empowering, especially in the face of uncertainty and information overload. Moreover, groupthink and social reinforcement play a significant role in perpetuating these beliefs. The internet and social media have created echo chambers where like-minded individuals can connect, reinforce each other's beliefs, and isolate themselves from dissenting viewpoints. This can lead to a hardening of beliefs and an unwillingness to consider alternative perspectives, even in the face of overwhelming evidence. In Section 7, titled Echoes in an Information Chamber, the Role of Social Media, we discuss how social media platforms have become breeding grounds for the spread of misinformation, including the flat Earth theory. Algorithms designed to maximize engagement often prioritize sensationalized content and create filter bubbles, where users are primarily exposed to information that aligns with their existing beliefs. This creates an environment where misinformation can thrive, as users are less likely to encounter dissenting viewpoints or fact checks. Furthermore, social media platforms often lack the gatekeeping mechanisms of traditional media outlets. Anyone can create and share content, regardless of its accuracy or veracity. This makes it difficult for users to distinguish between credible sources of information and misinformation. The rise of influencer culture also contributes to the problem, as individuals with large followings can spread misinformation to a wide audience, often without accountability or scrutiny. The decentralized nature of social media makes it challenging to combat the spread of misinformation. Content moderation policies vary widely across platforms, and efforts to flag or remove false information are often met with accusations of censorship. Moreover, the sheer volume of content makes it impossible to monitor and fact-check everything that is shared online. Section 8. Critical thinking in the digital age. Combating misinformation. In the age of information overload, critical thinking skills are more important than ever. Critical thinking involves questioning information, evaluating evidence, and forming independent judgments. It requires us to be skeptical of claims that seem too good to be true, and to be wary of information that confirms our biases. One important aspect of critical thinking is source evaluation. When encountering a claim online, it's crucial to consider the source of the information. Is it a reputable news organization, a peer-reviewed scientific journal, or an anonymous blog post? What is the author's expertise or agenda? Being able to assess the credibility of sources is essential for navigating the digital landscape and separating fact from fiction. Another important skill is recognizing logical fallacies. Logical fallacies are errors in reasoning that can make arguments seem persuasive even when they are based on faulty logic. Common fallacies include ad hominem attacks, straw man arguments, and appeals to emotion. By learning to identify these fallacies, we can avoid being swayed by misleading arguments. Section 9. The value of scientific literacy. Navigating a world of information. Scientific literacy is essential for navigating the complexities of the modern world. It empowers individuals to make informed decisions about their health, the environment, and technology. Scientific literacy involves understanding the scientific method, the process by which scientists ask questions, gather evidence, and draw conclusions. A scientifically literate individual is able to understand and evaluate scientific claims, even if they lack expertise in a particular field. They can distinguish between correlation and causation, recognize the importance of peer review, and understand the tentative nature of scientific knowledge. Scientific literacy also involves understanding the limitations of science and recognizing that scientific knowledge is constantly evolving. Promoting scientific literacy is crucial for combating misinformation and ensuring that individuals have the tools to make informed decisions. This requires investing in science education, supporting scientific research, and fostering a culture of curiosity and critical thinking. Section 10. Curiosity, the engine of progress. Curiosity is the driving force behind scientific discovery and human progress. It is the innate desire to explore, to question, and to understand the world around us. From the earliest humans who looked up at the stars and wondered about their place in the cosmos to the scientists today, who are pushing the boundaries of knowledge, curiosity has been the engine of our collective journey. Curiosity fosters a sense of wonder and a thirst for knowledge. It encourages us to challenge assumptions, to seek out new perspectives, and to embrace the unknown. Curiosity is not limited to scientists or academics. It is a fundamental human trait that can be nurtured and celebrated at all ages and in all walks of life. In a world that is constantly changing, curiosity is more important than ever. It allows us to adapt to new challenges, to embrace innovation, and to continue to learn and grow throughout our lives. By fostering a spirit of curiosity in ourselves and in future generations, we can ensure that the pursuit of knowledge continues to illuminate our path. Section 11. Beyond the Horizon, the never-ending quest for knowledge. The quest for knowledge is a journey without a final destination. As we explore the universe and delve deeper into the mysteries of the natural world, we inevitably encounter new questions and new frontiers to explore. The history of science is a testament to the never-ending nature of this pursuit, with each discovery paving the way for new inquiries and a deeper understanding of our place in the cosmos. From the subatomic particles that make up the fabric of reality to the vast, cosmic web of galaxies that stretches across unimaginable distances, the universe is full of wonders waiting to be uncovered. The more we learn, the more we realize how much more there is to know. This realization, far from being discouraging, is a source of inspiration and motivation for scientists and explorers across all disciplines. The pursuit of knowledge is not merely an intellectual exercise. It has practical implications for our lives and for the future of humanity. Scientific advancements have led to countless innovations that have improved our health, extended our lifespans, and transformed the way we live, work, and communicate. The knowledge we gain through scientific inquiry empowers us to address global challenges, such as climate change, disease, and resource scarcity. Section 12. Embracing the cosmos. Our place in the vast universe. In the grand tapestry of the cosmos, our planet is but a tiny speck. Yet it is on this pale blue dot that life as we know it exists, a testament to the extraordinary power of the universe to create complexity and beauty from simplicity. As we continue to explore the cosmos and unravel its mysteries, we gain a deeper appreciation for the preciousness of life and the interconnectedness of all things. The realization that we are part of something much larger than ourselves can be both humbling and awe-inspiring. It reminds us that our differences are insignificant in the grand scheme of things, and that we share a common bond with all living creatures on this planet, and perhaps beyond. This perspective can inspire us to live more meaningful lives, to cherish our connections with others, and to protect the fragile planet we call home. The universe is a vast and mysterious place, full of wonder and beauty. By embracing scientific inquiry, nurturing our curiosity, and never losing our sense of wonder, we can continue to explore the cosmos, unravel its secrets, and perhaps one day answer the ultimate question: what is our place in the universe?